Hello, I'm going to talk about Section 2.2, General Solutions of Linear Equations. So in this section, we introduce the idea of a linear equation with that is higher order, an nth order linear differential equation. Okay, so the first theorem you see there, if you're looking at your book on page 113, is about this idea of linear combinations of solutions to homogeneous equations. So let me do a couple of problems here, and then I'll allude to some of the concepts as I'm doing them. So, okay, first one I'm going to do is this. I just talk a little bit about the idea again of linear dependence and linear independence. So let's see here. Sorry. All right. So here we go. So this is problem number 5 that we're looking at here on the right. Okay. It says we're supposed to show that the functions f of x equals 17, g of x equals the cosine squared of x, and h of x is the cosine of 2x. We want to show those are linearly dependent. Okay, so this means we need to find these constants, C1. Here, I'll sort of point at where I'm at here. So we want to find these constants, these 3 constants, C1, C2, and C3, that have the property that we can write 0 as a linear combination of the 3 functions. And we want to show that we can do this in such a way that not all 3 of them are 0. Remember, if we can do that, then we will be able to solve the system of solve for one of the equations expressed as a linear combination of the other 2, and that's what we mean by linearly dependent. So here's a fact from trigonometry that we're going to use. I mean, the only way we're going to do this is to get some relationship between the functions, and this trig fact gives us a relationship between g of x, okay, and h of x over here. Okay, so using that, we can see that basically g of x is equal to h of x over 2 plus 1/2. Okay, well then what we can do is that means that g of x minus 1/2 h of x minus 1/2 times 17 times 1 over 17 equals 0. So what I've done there is I've simply brought the function f of x into the mix there by writing it as 17, then dividing by 17, effectively not changing the value of 1/2. So then you can see we have this nice expression that if I take minus 1/34 of f of x plus 1 times g of x, and if I add minus 1/2 times h of x, I get 0. So that means that these are linearly dependent. Okay, so what we're usually looking for in differential equations is a collection of linearly independent solutions, so that in fact we can try to write down the general solution to the differential equation, as we will see later. Okay, let's look at number 7. Now there's over here on the left, here I'll pull this up, what you're looking at here is a nice Wikipedia page. I recommend Wikipedia in general for mathematics. There are possibly errors somewhere within Wikipedia, but as the culture of mathematicians is so on this stuff, it's very rare that you will be able to find an error in a Wikipedia page. Okay, so what we're looking at here, this appears in your book, but is the definition of the Wronskian, and we're going to use this Wronskian to determine whether collections of functions are linearly independent or not. So let's do number 7 here from the homework. Okay. All right. Number 7. Let's get back up there. Add back up there. All right. Here we go. Okay. So for number 7. So what we have are these 3 functions: f of x equals 1, g of x equals x, and h of x equals x squared. We'd like to determine whether or not these 3 functions are linearly independent or if they are linearly dependent. Okay? So what we can do is we can use the Wronskian. So we will actually form the determinant of the matrix where I put f of x right here, g of x, and then h of x. Then the next row in this matrix that is that we're taking the determinant of is f prime is right here. This is g prime, and this is h prime. And then below that, we take the derivative of the row above it. So we get 0, 0, 2. Now from linear algebra, if we calculate the determinant, we can basically do it in the following way, where we have these, we expand across minors. In your college algebra class, you should have talked about this. So what we have here is this breaks down to just being 0 times, well, it would normally be 0 times the determinant that's formed by these 4 objects, minus 0, you have to have an alternating sum, there's times the determinant of the matrix 1, 0, x, 2x. So the only one that shows up is this 2 times the determinant of the matrix. So, oh, I see I've done a little error here, so let's correct this right away. So it's 2, it should be times the determinant that is obtained by the entries in the matrix that you get by eliminating the row and the column that the entry 2 is in. So that means that I have to change this up a little bit. Okay, no problem. I can. All right. Well, I'll get to that. There we go. Okay. So what we need here is we need to put a 1, an x is 0, and a 1. So the determinant of this matrix is just essentially 2 times 1 minus 0. So that's 2. Okay. Now that that is not 0. And since that is not 0, we can conclude that the functions in question, since they are analytic, is that in fact these are linearly independent functions over the real line minus infinity to infinity. Okay, so we'll be needing the ability to find linearly independent, determine the linear independence of functions in the future. Here's another. It looks like the same example. Okay. Okay, so here's number 17 as I wanted to do here. Sorry for that. I hope that sounds all right. A little editing I may have to do. So number 17, we have this differential equation. It's a third order differential equation. Okay, and what we are, there it is, and we have the initial conditions so that we know the value of the function at 0 is equal to 3. Its derivative at 0 is minus 1, and its second derivative at 0 is 2. So this is the initial value problem as stated. And we are actually given the solutions in the problem of the differential equation. We have y1, y2, and y3. So these are 3 linearly independent solutions to the differential equation. Now when we have a third order linear differential equation and we can find 3 solutions that are linearly independent, we then know that the general solution to the homogeneous equation is given as a linear combination of the 3 solutions. That's why y of x equals c1 times 1 plus c2 times the cosine of 3x plus c3 times the sine of 3x is the general solution. Now what I need to do to find the particular solution that satisfies the initial conditions is I need to actually find the derivatives of the function y. So that's what you're looking at here. There's the derivative of y and the second derivative of y. Using the initial conditions given in the problem, that is, right here, I sound like a recording, here and here, oops, sorry, we see that we need 3 to be equal to c1 plus c2 plus c3 times 0. That's what I get when I plug 0 into the cosine and the sine. If I plug 0 into the cosine of 3x, I get 1, and that's why c2 pops up right here. Hold on. Okay. Well, moving along here. Okay. We also get this right here, the second equation, and the third equation. Now, using elementary techniques for solving systems of equations, we see that we get the coefficients of that C2 is equal to minus 2/9 and C3 is equal to minus 1/3. And basically plugging those points back into the first equation, that is plugging C2 into the first equation, we arrive at C1 is equal to 21/9, and we now have the particular solution that satisfies the differential equation down here with those particular initial conditions. So that's number 17. Okay, so let's go up here. The final problem I'd like to illustrate here as an example in this section is the following. So we have this, this is a non-homogeneous differential equation. We have that, we have the 6 on the other side there, right? So y double prime minus 2y prime minus 3y is equal to 6. And we have the initial conditions that y of 0 is 3, y prime of 0 is 11, and we're supposed to find this y sub c, which essentially is the general solution to the corresponding homogeneous system. And then we're going to find y sub p, that would be one particular solution. And then it turns out via our theorems that if we add these two together, we will get the general solution to this non-homogeneous equation. And voila, we will then solve the initial value problem. So from the previous section, 2.1, we need to calculate and find the characteristic equation of this differential equation. That is done as it was in the last section by writing down r squared minus 2r minus 3 equals 0. This corresponds to the differential equation, which I'll call star. Okay, factoring that using techniques from elementary algebra, you find that r plus 1 times r minus 3, that must be equal to 0. Okay? By looking at it, you see the roots are r equals minus 1 and r equals 3. From the theory that we studied in the previous section, we now know that the general solution to the homogeneous equation is given as a linear combination of the functions e to the minus t and e to the 3t. That is, y sub c is the c1 e to the minus t. It's right here. Okay. So there's our general solution to the homogeneous equation. Now, what we're going to do is we're going to guess a solution for our particular solution. Because of the way that this looks, you might remember from our first homework assignment, a good guess would be a polynomial. Okay, so here's my polynomial. Y is ax squared plus bx plus c. And calculating the derivatives and substituting it back into the differential equation, one can see, blah, blah, blah. This is a little messy, but the bottom line is it's easy to see if you look at a has to be 0 because there is no quadratic term in the number 6. Similarly, because a is 0, b must be 0 because there is no linear term in this in the number 6, or the coefficient of x in that polynomial has to be 0. And so we can see that since 2a minus 2b minus 3 times c is 6, that forces c to be equal to minus 2. Okay, so putting this all together, we then see that the general solution to that differential equation is given right here. In other words, we take our general solution to the homogeneous equation and add to it the particular solution. Now, what you see following here are is the solution of the initial value problem. I differentiate the function y here, and then I evaluate using the initial conditions. I see that 3 has to be c1 plus c2 minus 2, and 11 has to be minus c1 plus 3c2. Then solving what you're seeing here, I've solved the system of equations, and I arrive at the conclusion that C2 is equal to 4 and C1 is equal to 1. So therefore, the solution to the initial value problem is given right here. and that is y of x equals e to the minus t plus 4 e to the 3t minus 2. Okay, so you can go through this video. This video should give you a fairly good explanation of some of the techniques that are illustrated in section 2.2. If you have any questions about what the techniques are, please feel free to give me a call. We'll set up a online little office hour here. So I hope that this has been helpful. Thank you.